In section 4.5, we're going to be talking about L'Hopital's rule, which is a technique to evaluate limits. Now, before I talk about what L'Hopital's rule states, we're really going to focus on whether our limit is an indeterminate form or a determinate form. So I'm going to list here all the indeterminate forms. Indeterminate forms. There are 7 total indeterminate forms. The first 2 are indeterminate quotients, 0 over 0 and infinity over infinity. Now, this is the limit of a function, like the limit of f of x goes to 0 and the limit of g of x goes to 0. So we're taking the limit of one function over another. And if both functions are going to 0, this is what we call an indeterminate form. Or if both functions are heading to infinity, we call this an indeterminate form. And what we mean by that is that the answer isn't always the same, right? Because functions will head to 0 at different rates. Okay, x cubed goes to 0, or actually let's do the infinity. Okay, x cubed goes to infinity much faster than a square root, right? And so we're kind of looking at comparing as how fast these functions are going to infinity or how fast these functions are heading into 0. So if the top function goes to 0 faster than the bottom function, then we will get 0 as a result. Okay? If the bottom function heads to 0 a lot faster than the top function, we're going to get an infinity result. And if they head to 0 about the same rate, we're going to get some finite number. So in both of these cases, the answer could be 0, the answer could be infinity, or the answer could be any number in between, right? Even negatives. So to contrast these indeterminate quotients, I would like to look at determinate quotients. Determinate forms. If you get these forms, the answer is always the same. Okay? So anytime one of your functions heads to a constant, it's almost always a determinate form, right? So I'm going to use 1 as our constant. So if we get 1 over 0, okay, that means the limit of our top function went to a constant. So 1, 5, 10,000, okay? Our bottom function went to 0. Well, what happens when a function heads to 0, right? What happens when the denominator gets smaller and smaller and smaller? 1 over 1,000,000, 1 over 2,000,000, 1 over 10,000,000, right? This number is really large, right? Not 1 over 1,000,000, 1 over 1 over 1,000,000, right? 1 over 10,000,000. So what happens when this gets really small, the fraction gets really large? This is always determinate, guys. And the answer is going to be infinity, always. So what happens if we get 1 over infinity, right? So what if our top function heads to 1 or some other constant, and our bottom function heads to infinity? Okay, if the denominator gets really large, then the fraction gets really small. And this determinate form is always 0. Right? If we were to mix these, if I were to get 0 over infinity here, right? If the top function headed to 0 and the bottom function headed to infinity, okay, this is making the limit go to 0, and if we were to look at the bottom of the denominator going to infinity, that makes this fraction go to 0 as well. So it's kind of going to 0 doubly. And so this limit is going to be 0. It's a true definition of 0. Okay? The top's going to 0, the bottom is making that fraction go to 0. So if I were to do infinity over 0, if the top function was headed to infinity and the bottom function was headed to 0, okay, this is like infinity times 1 over 0. 1 over 0 is the truest definition of infinity we have, okay? And so this is infinity. 1 over 0 is infinity. If the bottom is getting really small, the fraction is getting really large. And so this determinate form is always, always, always infinity, okay? So we're going to kind of always check to whether we have a indeterminate form here or one of these determinate forms here before we evaluate the limit. All right, our third indeterminate form is our indeterminate product. So there's only one indeterminate product, and that is 0 times infinity, okay? Or infinity times 0. The infinity could be plus or minus, right? But if you were to have a function, if the first function, say this is f of x and this is g of x, if the limit of f went to 0 and the limit of g went to infinity, okay, it depends on which one's going faster. Is the function heading to 0 faster than the function heading to infinity? Well, if it's going to 0 faster, the answer is going to be 0. If this function is heading to infinity a lot faster than this function is heading to 0, then the answer is going to be infinity. If they're heading to their respected values, okay, 0, infinity at the same rate, then their product is going to even out, and it's going to be some finite answer, okay, 1, 2, 5, 8, okay, it's just some finite number, right? So here's our indeterminate product. Now, just to put some determinate ones here, 0 times a constant, okay, still 0. Some constant times infinity, still infinity, right? 0 times 0, still 0. Infinity times infinity, still infinity, all right? So, 0 times a constant, we're always going to get 0. Infinity times some constant, we're always going to get infinity. And if we have 0 times 0, answer still 0. If we have infinity times infinity, answer still infinity. Okay. And if one of these happened to be going to negative infinity, we would just use our rules of signs as needed, right? So sometimes our answer will be negative infinity. But the only product you have to worry about is 0 times infinity. All right, the fourth indeterminate form is our indeterminate difference, okay, and that is infinity minus infinity. Infinity minus infinity is not 0, because you have to remember that this is the limit of a function heading to infinity, and this is a limit of another function heading to infinity. So which function is heading to infinity faster? Okay, or are they heading to infinity at about the same rate? And so we'll get some finite number here. Okay, are they heading to infinity at exactly the same rate? And we're going to get 0. Okay, so indeterminate. This answer could be 0, it could be infinity, it could be some finite number. It could be anything. All right. So some helpful determinate forms to kind of compare their indeterminate to our determinate, some things we still know. If we do 0 minus infinity, if the first function is going to 0 and the second one's going to infinity, we are going to get negative infinity. Okay. If we had negative infinity minus positive infinity, okay, so if we had minus infinity, notice both of our infinities are negative. This is going to head to negative infinity. Okay, there's no way around it, right? If we had infinity minus 0, we would get infinity. If we had infinity minus a negative infinity, right, notice that this really becomes infinity plus infinity, which is infinity, right? So we have some determinate differences here that we know the solutions to, right? Only one indeterminate difference. Now, the last three indeterminate forms are powers, and I'm probably going to do a separate video there, all right? But our indeterminate powers, just so you'll have them all in one location, they are 0 to the 0, infinity to the 0, and 1 to the infinity, okay? So we're going to have a function raised to another function. So if we have 0 to the 0 power, okay, I know you learned that anything to the 0 power is 1, but that's just simply not true. The base, A, has to be greater than 1, all right? Or actually, it just has to be greater than 0. It always says A is greater than 0, all right? And so that 0 exponent rule kind of doesn't work here, okay? Same thing with infinity, okay? If our bottom function is headed to infinity and the exponent is headed to 0, this is indeterminate, right? And then this is really weird to think about. So the limit of the base function here is 1, okay, but it's headed to 1, all right? So it's not really a true 1, right? And this function is headed to infinity. So when we look at a limit heading to 1, okay, it's not exactly equal to 1. So we get like, 0.9 to the infinity power, or 0.95 to the infinity power. And that difference between the limit value and the actual true 1 value gets amplified as this function is headed to infinity. So you think you have like 1 times 1 times 1 times 1 times 1 infinite times here, but you really don't. You have 0.95 times 0.95 times 0.95 times 0.95. And so if you do that to infinity, that difference kind of gets amplified, right? And you don't always go to infinity. So all three of these are indeterminate. 2 with a 0 exponent and 1 with an infinity exponent, right? So I'd like to kind of explain to you why these are indeterminate. And the best way I can explain this, and this is how we're going to solve these, is what were to happen if we were to ln these. All right. So if I ln 0 to the 0 power, then I can use that third logarithmic rule to pull that 0 out front. So I get 0 times ln of 0. Right? Now 0 times ln of 0 is an indeterminate product, right? Because ln of 0, if you were to look at your calculator, the ln function has a vertical asymptote, right? So we're really getting 0 times negative infinity here, which is an indeterminate product. And so because this power turns into an indeterminate product, this power is indeterminate, right? And that's what's going to happen on each one of these. So if I were to ln infinity to the 0 and use that exponent, that third law of exponents, and bring the 0 out front, I'm going to get 0 times ln of infinity. Right? Now ln of infinity, here's my ln function, right? And as x goes to infinity, this function is going to infinity really slowly, but it's still headed there. So this breaks down into an indeterminate product, 0 times infinity. Okay, so because this is an indeterminate product, this is an indeterminate power. Same thing's going to happen for the 1 to the infinity. Right? If I were to ln this function and use that third law of logarithms and pull the infinity out front, I get infinity times ln of 1. Right? So infinity is infinity. Ln of 1 is the x intercept there. Ln of 1 is 0. So we're going to get infinity times 0, which, lo and behold, is another indeterminate product. Right? So all three of these powers when ln is applied, it becomes an indeterminate product. Right? So that's how we're going to keep those straight. So some determinate powers here. You really want to watch out. Okay? So 1 to the 0, all right, is still 1. Okay? Any constant to the 0 power is 1. It just can't be 0 or infinity. Right? 1, oh, see, actually I can't do 1 to the infinity, right? Let's do infinity squared, right? If I get infinity to a power, we're still going to get infinity. How else can I mix these up? Oh, let's do 0 to the infinity, right? This is actually, if I were to ln this, I would get infinity times ln of 0, which is infinity times negative infinity. But you might watch out here, we might get positive or negative infinity, okay? But it is determinate. It is one of the infinities. So we'd have to look at those functions to see exactly what's happening there. What else can we do? 0 to the, no, I just did 0 to the infinity. Infinity to a constant. I'm struggling to come up with all the determinate forms here, but you get the drift. These are indeterminate, okay? These are determinate. We're always going to make sure we get indeterminate forms before we go any further. All right, so let's go ahead and look at what the L'Hopital's rule says, right? Now, even though there's 7 indeterminate forms, L'Hopital's rule can only be applied to the first 2. Right? We can only use L'Hopital's rule if we get 0 over 0 or infinity over infinity. All these other indeterminate forms require us to change its form to an indeterminate quotient before we use L'Hopital's rule. So we're going to look at examples of all of these, but first let's just focus on our indeterminate quotients. All right, so L'Hopital's rule. Very, very handy. Very nice. Okay, this is applicable even to the beginning of the semester. So of course that's why we're doing it last here. But this is a useful way to determine limits that were previously we had to do a table or a factor or divide by the highest powered x in the denominator. Okay, we used a lot of strategies, but really L'Hopital's rule was our end-all rule that we needed to use. All right, so if the limit as x approaches a of f of x equals 0 and the limit as x approaches a of g of x equals 0, okay, or so both f and g have to be heading to 0, okay, or both f and g limits head to infinity. Okay, plus or minus here. Then the limit as x approaches a of f of x over g of x. Right, so we're going to look at this function here, and we're going to do the limit of the top and the limit of the bottom. And if both the top and the bottom go to 0, or if both the top and the bottom go to infinity, we have an indeterminate form. All right, if the top and the bottom, form one of these determinate forms, we don't use L'Hopital's rule. Okay, L'Hopital's rule will give us a false result. But if they both go to 0, or if they both go to infinity, L'Hopital's rule says that the following is equal. Okay, so these aren't truly equal, so I am going to put an L'H above the equals, kind of stating that I'm using L'Hopital's rule. And they're equal to the derivative of f over the derivative of g. And most of the time, this is simpler. Okay, this will help fix our indeterminate process there. my computer stuff. Okay. And so if this is still indeterminate, we can use L'Hopital's rule again, all right? And keep using L'Hopital's rule on all of our indeterminate quotients. Now I want you to notice we are taking the limit of a quotient here, all right? But when we use L'Hopital's rule, we're not using the quotient rule, right? We're not doing the derivative f times g minus the derivative g times f all over g squared. This is not a quotient rule here, right? We're just taking the derivative of the top and putting it over the derivative of the bottom, right? So let's do a few examples of the L'Hopital's rule. Okay. All right, so here we have the limit as x approaches 3 of x minus 3 divided by x squared minus 5x plus 6. So I hope this is indeterminate, right? So we're going to test it. Now I know we can factor this and reduce it and evaluate it that way, but let's just see if we can apply L'Hopital's rule. So we got to make sure we get 0 over 0 or infinity over infinity. All right. So if I plug 3 into the top is definitely going to give me 0. If I plug 3 into the bottom, 9 minus 15 is negative 6. Negative 6 plus 6 is 0. Okay. So we do get 0 over 0. This is what I'm going to start calling L'Hopitalable. Right? We can apply L'Hopital's rule here. So I am going to apply L'Hopital's rule. And L'Hopital's rule says that it's equal to the limit as x approaches 3. And then I'm just going to differentiate the top. Right? The derivative of x minus 3 is 1. And the derivative of x squared minus 5x plus 6 is 2x minus 5. Right? So what happens here is now that we have a constant up top, it's no longer indeterminate, right? Anytime we get a constant, we have a determinate form. So if I evaluate 3, or if I evaluate the bottom at 3, go ahead and plug 3 in, I get 6 minus 5 on the bottom, so I get 1 over 1, which is 1. Okay, so the limit of this function is 1. 0 over 0 in this case is 1, which means that both these functions are heading to 0 in a 1-to-1 ratio, right? So I guess near 0, both x, let me go ahead and show you this. Near 0, let me do it over here. Here's my x squared, and here's my x. They're headed to 0 in a 1-to-1 aspect. Okay, they're kind of headed to 1 at about the same rate, right? And so we're getting 1 as a result. All right, so if I were to use the same function here and look at the limit as x goes to infinity of the same function. So remember, this is kind of how we determined whether a function had a horizontal asymptote or not, right? The limit as x goes to infinity. What is this function doing on the outskirts? Is it approaching a number or not? So this tests for asymptotes. And the rule is, if the top is lesser degree than the bottom, then we have an asymptote at 0. So after I apply the L'Hopital rule here, I want to make sure to verify that we're getting the right result, right? So if I were to see what form this is, I am going to plug infinity in for x, right? Infinity minus 3, still infinity, right? Infinity squared minus 5 times infinity plus 6 is still infinity, okay? And so we get this indeterminate form, infinity over infinity, so we can L'Hopital this. Right? It's L'Hopitalable. So I'm going to apply L'Hopital's rule, which says we're going to use the same limit, but we're going to do the limit of the derivatives. Right? So the derivative of the top is 1. The derivative of the bottom is 2x minus 5. And as soon as we get a constant up here, it's no longer indeterminate. This is a determinate form, right? So 1 over, if I let x go to infinity, I'm going to get infinity minus 5, which is still infinity, right? So now I get this form 1 over infinity. And remember what happens here. If the denominator gets really large, then the fraction gets really small. 1 over infinity is 0. Okay, so hence, this function should have a horizontal asymptote at 0. All right, so let's just go ahead and work a few more examples, right, using L'Hopital's rule on these quotients. So let's do the limit as x heads to infinity of ln of x over x minus 1. Oh wait, so which form is this? That's the first thing we have to determine. Okay, if we plug infinity in there, what are we going to get? All right, so ln of infinity. What is ln doing as x heads to infinity? You really have to get the graph of ln kind of memorized here. So remember, ln has a vertical asymptote and it goes up and out, okay, gradually forever. So as x heads to infinity, this ln function is headed to infinity. Right? So the top is going to infinity. The bottom, infinity minus 1, is still infinity. Right? So we get this indeterminate quotient, and we can L'Hopital indeterminate quotients. So we're going to evaluate the same limit. Right? But we're going to do the derivative of the top over the derivative of the bottom. So the derivative of ln of x, the derivative of the argument over the argument, so we're going to get 1 over x for the derivative of the top. The derivative of the bottom, the derivative of x minus 1 is just 1. Right? So now we can evaluate this limit. Right? We have 1 over x, basically. So if x goes to infinity, we're going to get this determinate form, 1 over infinity, which is indeed 0, just as it was before. All right, let's go ahead and do the limit as x heads to 0 of 2 sine x over x. All right, so is this indeterminate? If you plug 0 in, okay, well, you get 0 over 0, infinity over infinity. So if I were to plug 0 in here, sine of 0 is 0. 0 times 2 is 0. If I plug 0 in the bottom, obviously we're going to get 0. Okay, so this is indeterminate, right? 0 over 0. So let's go ahead and L'Hopital this function. Right. So the derivative of the top, the derivative of 2 sine x, is just a constant times sine. So the derivative is going to be the constant times the derivative of sine. So we're going to get 2 cosine x here. The derivative of x is 1. Here's that constant. Right? As soon as we get this constant, we have a determinate form. We're going to have a solution. Right? So if I let x go to 0, cosine of 0 is 1. So we're going to get 2 times 1 here, which is 2. All right, so let's look at this one. The limit as x approaches 0 of e to the x minus 1 minus x all over x squared. Okay. So what would happen if we evaluated this limit at 0? Okay, e to the 0 is 1. 1 minus 1 is 0. 0 minus 0 is 0. The top is 0. 0 squared on the bottom, so that's 0, obviously. So we do get this indeterminate form 0 over 0. So we're going to apply L'Hopital's rule and use the same limit. And we're going to take the derivative of the top. Okay, the derivative e to the x minus 1 minus x. So the derivative e to the x is e to the x. The derivative minus 1 is 0, and the derivative minus x is minus 1. Okay. The derivative of the bottom, the derivative of x squared is 2x. So what happens if we plug 0 in there? Okay. We're going to get e to the 0, which is 1. 1 minus 1 is 0. Uh-oh. The bottom is also 0. Right? So it's not that L'Hopital's rule didn't work. It's just we still have an indeterminate form. Right? So if we have an indeterminate form, we can just apply L'Hopital's rule again. And just keep applying it until you get a determinate form. So let's go ahead and take the derivative of this function. Right? So the derivative of e to the x is e to the x. The derivative of minus 1 is 0, so it's going to go away. The derivative of the bottom is 2. Right? So here's our constant. As soon as we get this constant, we have a determinate form. Right? I know the solution is coming. So if we plug 0 in for x, we're going to get e to the 0 over 1, which is 1 over 2. Okay, so we're going to get a 1/2, right? And I do believe that that means that this function, x squared, is going to 0 twice as fast as this function. All right, let's look at a more complex one. Okay, to finish out this video here, let's do the limit as x approaches 0 of tan x minus x over x cubed. Okay. So you have to kind of remember what tan of 0 is. Okay, tan of 0, I mean, if you wanted to use the unit circle, you could. Right, the point on the unit circle, x is 1, y is 0. Tangent is sine over cosine, so we're going to get 0 over 1. So tan of 0 is 0. 0 minus 0 is 0. 0 cubed on the bottom is 0. Right? So we do get this indeterminate 0 over 0 form. So I am going to use L'Hopital's rule. And take the limit as x approaches 0 of the derivative of the top. So the derivative of tan x, secant squared. The derivative of minus x is minus 1. And then the derivative of the bottom is 3x squared. Right? So did this help? Okay. Did it clear out our indeterminate form? So if I plug 0 now into this function, secant squared of 0. So we're still at an angle of 0, right? Secant is the reciprocal of cosine. So secant of 0 is 1, right? Because cosine is 1, the reciprocal of 1 is 1. Secant squared is going to be 1, right? So we're still going to get 1 minus 1, which is 0 on top. And we're still going to get 3 times 0 on the bottom, right? So we still have an indeterminate form. So let's go ahead and L'Hopital this again. Now, in order to take the derivative of secant squared, you have to see this as a chain rule, okay? Or see it as a product rule, secant times secant, right? But I am going to kind of outline a chain rule here. So I'm going to do secant x squared, right? And then the minus 1 is just going to go to 0. So I'm just going to forget about it. All right, so A is my outside function. B is the inside function. The outside function is x squared. The inside function is secant x. Take the derivative of the outside and the derivative of the inside. The derivative of the outside is 2x. The derivative of secant x is secant x tan x. And so to use the chain rule, we're going to plug b into a prime and multiply times b prime. So we're going to get 2 times secant x tan x. All right, so I'm going to get 2 secant x times secant x tan x. Ooh, I ran off my paper. Okay. And then the derivative of 3x squared is 6x, right? So I probably should have wrote secant squared here, but if we evaluate this limit, okay, we're going to get, if we plug 0 in, secant of 0 is 1, secant of 0 is 1, tan of 0 is 0, so 2 times 1 times 1 times 0 is still 0, right? And then if I plug 0 in here, I'm going to get 0. So I do have a indeterminate form, 0 over 0. Now, I have like 3 products, right? A product rule of 3 functions here. So I'm going to opt to not just differentiate this with these 3 functions here, which it probably would work, but I'm going to simplify this, right? And I'm going to simplify the functions that don't go to 0, or separate the functions that don't go to 0 from the functions that do, all right? So the function that goes to 0 is tan x, right? 2 times secant x does not go to 0. And here, 6 doesn't go to 0, it's the x that goes to 0. So I'm going to separate this, okay, and do the limit, and separate this product and do the limit of the first times the limit of the second. Right, so I'm going to get the limit as x approaches 0. I'm going to separate 2 secant x over 6 from the limit of tan x over x. Okay, so I'm just splitting this product and doing the limit into the product of 2 limits, right? The limit of a product is the product of the limits. It's one of those limit laws that we went over. So if I let x go to 0 here for this limit, secant of 0 is 1, and so we're going to get 2 over 6, which is basically 1/3. Right? We're going to get 1/3 for this limit here. Right? For this limit, we're going to get 0 over 0, which I need to evaluate using L'Hopital's rule. So I am going to kind of do it on this line here, but no, we're just using L'Hopital's rule to evaluate the second limit. So I'm going to do the limit as x approaches 0, the derivative of tan x, secant squared. The derivative of x is 1. Ooh, we're done because we get this constant down here. All right. So we're going to get the limit as x approaches 0 of secant squared over 1. So secant of 0, for a millionth time today, is 1, right? You're going to see that a lot. So secant of 0 is 1, 1 over 1 is 1. So we're going to get 1/3 times 1, which is 1/3, right? Which means that x cubed goes to 0 3 times faster than tan x minus x, right? So this is how to evaluate the limit of indeterminate quotients. Right? So the next video I'll tackle the differences in the products, and then the final video we'll tackle the indeterminate powers.